All right, everybody, so this is going to be our last lesson on transformations, and we're going to finish with a collection of examples that feature all of the different transformations kind of mixed together that we've talked about. And you'll notice for our first example and our second example, I included the same instructions. So for both examples, we're going to describe the transformations, we're going to sketch the graph, we're going to determine the domains and the ranges of the function and the transformed function, and then we're going to talk about coordinate analysis. Okay, so here we are. Our original function is f of x equals x squared. That's a function that we've grown very familiar with by now. And then our transformed function is 3 minus 2x squared. What many of you will find helpful is rather than writing 3 minus 2x squared, rewriting it as negative 2x squared plus 3. You may not need this, but it may help you see more clearly what the transformations are that we're working with. I'm going to circle them in red. So we have the negative on the outside, we have the 2 here, and we have the plus 3. So describing them in order. So we have the negative on the outside, that's a reflection in the x-axis. The 2 on the outside is a vertical stretch. So I'm going to write here a vertical stretch by 2. And then the plus 3 on the outside, that's a vertical shift by 3. Notice that for the shift and the stretch, I'm specifying that it's vertical, and I'm specifying by how much it is. So it's not enough to just say stretch and shift. You need to specify that it's a vertical stretch by how much. For the shift, you could also say shift up 3 if you find that to be quicker. That means the same thing, but make sure to specify what direction you're shifting and how much. Now, much like I've done before, I'm going to do sort of a few key points. So we're going to start with 0, 0 as our vertex. Then we'll look at 1, 1. And we'll also look at negative 1, 1. I'm not using these 3 points for any particular reason other than they're really easy to plot and the coordinates are nice and small. If you want to do more points for yourself, you are welcome to do that. I'm just picking these 3. Part of the reason I'm picking them is that they are really good at defining the shape, that parabolic shape that we're looking for. Okay, I'm actually going to go ahead and start with 1, 1, and I'm going to do the transformations on it. So first, we reflect in the x-axis. So check it out. Reflecting it in the x-axis takes us down here. So at this moment, we're at the point 1, negative 1, and we finish the reflection. Vertical stretch by 2. Vertical stretch by 2 is going to double our y coordinate. So starting at 1, negative 1, we're going to go down to 1, negative 2. And then from there, a vertical shift up by 3 takes us back and adds 3 to our y coordinate. So what's kind of neat, we haven't seen this before, is that even though we have 3 different transformations acting here, the end result is that we end up back at the point 1, 1. Okay, next, let's do the origin. It's a little bit goofy, like it's a little funky, but it's really good to talk through. So because the origin is on the x-axis, when you reflect it in the x-axis, it doesn't go anywhere. It stays put. By that same token, with a vertical stretch by a factor of 2, you are doubling the y-coordinate. But since your y-coordinate is 0, it stays 0. So neither one of the first 2 transformations have an impact on the origin. But then we're going to we're going to shift up by 3. So the new point is this one here, and that's 0, 3. Let's walk through negative 1, 1. So we reflect in the x-axis. We land here. We're at -1, -1. Then we vertical stretch by 2. So that doubles our y-coordinate. That takes us down to -1, -2. And then from there, we add 3 to our y-coordinate. So we end up back at -1, 1. So -1, 1 is also not ultimately moved by these 3 transformations. Just so that you don't start to feel confused, let's walk through another point transformation. We'll do 2, 4, and this one we'll just talk through. So 2, 4 would get reflected in the x-axis, which would negate its y-coordinate. So it would take it to 2, -4. That's the reflection in the x-axis. Then a vertical stretch by 2 takes me to 2, -8. And then lastly, a shift up by 3 adds 3 to my y-coordinate. So the 0.24 gets transformed to the 0.2, -5. You can see that's outside of the scope of my picture, but you can see that it's quite a ways down. So what that shows us is when you go to graph in the whole shape, it's still a parabola, but it's quite a bit steeper than the original red one that we started with. So when you look at the graph, you actually see all of the transformations. The fact that the blue parabola is significantly steeper than the red one, that's the vertical stretch. The fact that the parabola opens down as opposed to the red parabola, which started opening up, that's the reflection in the x-axis. And then the fact that the vertex of the parabola used to be the origin, but now it's up at 0, 3, that's your vertical shift by 3. So once you start getting more and more comfortable, you're going to be able to anticipate what all of these things look like, even without doing a point by point by point analysis. You're going to sort of see in your mind's eye what this is all going to look like. But there's no telling when that'll happen, so we're not going to worry about it. Let's very quickly talk through domain and range. So in black, I'm going to do the domain and the range of f, and then in blue, we'll do the domain and range of g. So this is the quadratic. So the domain is just all real numbers. And the range starts at 0 and goes up to infinity. For the blue function, the domain is still all real numbers. None of the transformations we work with would take an all real number domain and make it not be all real numbers anymore. Okay, so you don't need to worry about that. If you started with a function whose domain is all real numbers, you will finish with a function whose domain is all real numbers. Now for the range though, the range is now everything up to 3. The graph does not go above 3. And so in the range, you actually see both the vertical shift and the reflection in the x-axis. You see the range is flipped over and it is now up to 3 rather than stopping at 0. And finally, the coordinate analysis. So for this, I'm going to go back to the graph. We're going to pick some random point x, y. And we're going to talk through the transformations much like we did for 2, 4. So a reflection in the x-axis flips the y-coordinate. So after the reflection, we are now at the point x, -y. A vertical stretch doubles the y-coordinate, so it becomes x, -2y. And then lastly, the vertical shift by 3 adds 3 to the y-coordinate. So I'm actually going to write it here to make it a little more kind of final and clear. The point x, y on the original function lands at the point x, -2y plus 3, which may be a little bit nicer, is 3 minus 2y. So every single point on the graph of f transforms into that point on the graph of g. Again, there will come a time when you're more comfortable with this topic and you're able, without doing the graph first, without doing it point by point, just by listing the transformations, you're going to be able to list the coordinate analysis. This is something we build towards. It's not something that's expected right away. So for example 2, I left it blank because I wanted to talk through it with you. So we're starting with the absolute value of x. And we have, for g of x, I want to look at the absolute value of 1/2 x plus 3. Okay? And then just for fun, let's stick like a -2 on the outside. Okay, so here's what I'll do. I want to point out to you that you have 3 transformations happening here. The 1/2 being multiplied by x, that's going to be a horizontal stretch. This plus 3 is going to be a shift to the left, and this -2 is going to be a shift down. But before we go into writing all that out, I want to point something out to you, which is that both the horizontal stretch, which is that 1/2, and the plus 3 impact the x coordinate. And we want to pay attention to the order. With the y coordinate, the order is very intuitive. We almost don't think of it. We just kind of do them in the order that we think of them. But for x coordinates, you want to be a little bit careful. So what a lot of you are going to find helpful is rather than writing it as the absolute value of 1/2 x plus 6, sort of factor that 1/2 out. If you factor the 1/2 out, in other words, you're dividing 1/2 out there, it'll be 1/2 times the quantity x plus 6, and then -2. The reason this is helpful is that it shows you that if you do your compression first, the shift is not going to be by 3 units, it's going to be by 6 units. So look, we're going to write this out. We have here a horizontal stretch by 2. We have a shift left, right? So we're replacing that x with x plus 6, 6 units. And then after that, we have a shift down. So I wanted to make sure to include one example where we had transformations that impact the x coordinate and also the y coordinate. Okay, here goes. So again, I'm going to do a few points here, and you can do more if you want. So let's do 1, 1, 0, 0, and -1, 1. And then just to say we did, let's also do -2. No, let's do 2, 2. Okay. -2, 2 you could also do, but I think it'll be a little bit beyond the scope of our graph. Okay, so here we go. So first we have a horizontal stretch by a factor of 2. What that means is that we are going to multiply our x coordinate by 2. Let's start with -1, 1. So -1, 1, when we multiply our x coordinate by 2, it goes out to -2, 1. Oops, sorry. It goes out to -2, 1. So it lands up here. Okay, so there's -2, 1. Then we're going to shift left 6 units. So -2, 1 goes all the way over to -8, 1. And then lastly, shift down 2. So that's going to go down to negative 8, negative 1. Next, 0, 0. So the horizontal stretch, that doubles our x-coordinate, and doubling 0 doesn't do anything, okay? But for the horizontal stretch piece, it stays put. However, for the shift left, it's going to go over to negative 6. Okay. And then finally down 2. That's going to go down 2 units. And there's our final point there. Negative 6, negative 2. For 1, 1, first, the horizontal stretch. So that doubles our x-coordinate. So that lands here at 2, 1. Then shift left 6 units. So that takes us here. If you start with a point whose x-coordinate is 2 and shift left 6 units, that lands you at negative 4. And then down 2, that takes you here. So the final point there is negative 4, negative 1. And let's do again 2, 2. You'll see my graph is getting a little claustrophobic, so I'm starting to worry a little bit that this is too much, but that's okay. So 2, 2, we're going to double the x-coordinate, so we're at 4, 2. Then we're going to shift left 6 units, so that takes us to negative 2, 2. And then we're going to go down 2 units, so that takes us here. That's the point negative 2, 0. I'm not going to label it just because my picture is already pretty cluttered. So watch. There is my graph. It's also a V shape. But you can see it is significantly wider than, and I'm going to put a little arrow here just so we can see that this goes on forever. So this blue V is significantly wider and more open than the one that we started with, okay? Now, let's talk about the domain and the range. So the domain of the original function, I'll write that in black, that's all real numbers. So that's not going to be particularly exciting. The range, again, is from 0 to infinity. For the new function, the domain is still all real numbers. Again, that's never going to change. And the range is now from negative 2 to infinity. Okay? So you can see that the shift down impacted the range. Now let's talk about coordinate analysis, and I'm going to do it just the way that I did with the last example. So let's say that you started with some random point x, y. So for x, y, the horizontal stretch doubles the x-coordinate, so it becomes 2x, comma, y. The shift left 6 units takes us to 2x minus 6, comma, y. And then lastly, the shift down 2 units subtracts 2 from our y-coordinate. So it takes us to 2x minus 6, y minus 2. So meaning, if you start with a point x, y on the graph of f, that lands you to the point 2x minus 6, comma, y minus 2 on the graph of the function g. So what we see here is that when you have both a horizontal stretch and a shift horizontally, it matters which you do first. So for our purposes, we are going to take as our sort of golden rule of thumb that we do the horizontal stretch first, and that impacts the amount by which we shift horizontally. And I think the easiest way to see this in terms of like algebra is take the coefficient in front of x when you have one and factor it out like we did here. That's what showed us that after we did the horizontal stretch, our shift is by 6 units, not by 3. So that's all that I have for you in this lesson. And this concludes our conversation on transformations. Of course, if you have further questions on transformations, don't hesitate to post a discussion. I will absolutely help you further, and I will see you soon. Bye.